So good morning, students. So I think I have solved this problem. If I may remember this problem, I think I solved it in the previous class. Okay. So I will take up one more problem in the hydrodynamic lubrication. Can any one of you read the problem? Hmm. Who will read the problem? Praful TN. Just read the problem.
A bearing used for light-duty compressor has a load of 1 kilonewton, and oil used is SAE 60, and mean effective temperature of operation is 40 degrees Celsius. The journal has a diameter of 50 mm, and the bearing diameter is 50.05 mm. The speed of the journal is 15,000 rpm. The L by D ratio is limited to 1.2. Obtain the coefficient of friction and power loss by Petrov's analysis.
Okay, fine. Thank you. So again, this is a problem on lightly loaded bearing. So whenever lightly loaded means you should consider Petrov's equation for solving the problem. So one thing, I think I have solved this problem in the previous class. Is it not? Clearance 50.05, I have solved this. Okay. So I will take up next problem. This I have not solved. Okay. A full journal bearing has the following specification. Journal diameter is 70 mm, bearing length is 55 mm, radial clearance is 0.055 mm, and journal speed is 2200 rpm. Radial load is 1.1 into 10 raised to 3 Newton. See, all of you put your USN in the chat box. Don't forget to put your USN in the chat box. Okay. So assuming the bearing to be lightly loaded and power loss as the bearing is 3.3 kilowatt, determine the viscosity of the lubricant at effective temperature and the coefficient of friction at operating condition. See, look at this radial load given in the problem is 1.1 into 10 raised to 3 Newton. So during stating the definition of the lightly loaded bearing, I said that a load which is equal to 1 kilonewton or less than 1 kilonewton, that case is considered to be lightly loaded bearing. But in this case, the load given is 1.1 into 10 raised to 3 Newton. That is 1.1 kilonewton. It is exceeding 1 kilonewton. So that's what they have mentioned, clearly mentioned in the problem that, so you have to solve this problem assuming it is a lightly loaded bearing. Strictly speaking, it will not fall under the category of lightly loaded bearing. But in the problem itself, they have told to solve this problem assuming it as a lightly loaded bearing. See that, okay? So since they have insisted to solve this problem as a considering as a lightly loaded, we'll go ahead with the problem instruction. One more thing, power loss is given 3.3 kilowatt. Earlier problems, we used to determine or calculate the power loss with the given data. In this case, they have given the power loss, and in turn, you need to find out the viscosity and the coefficient of friction. So just like reverse engineering. Okay. So with the given data means a general diameter is given, that is 70 mm, bearing length is 55 mm, radial clearance, that is the difference between diameter of bearing to the journal, that is radial clearance, it is 0.055 mm. General speed is 2200 rpm, and load is 1.1 into 10 raised to 3 Newton. So just to list out the given data, find out the radial clearance is given in the problem itself. Okay, so diametrical clearance is 2 times of radial clearance. So 2 into 0.055, that is 0.11 millimeter. And the diametrical clearance ratio, it is capital C over small d. So it is 0.0015. So with the radial clearance, we got a diametrical clearance and a diametrical clearance ratio. Then the speed, n dash is equal to 2200 divided by 60. That is 36.67 RPS. So converting RPM into second. And then the radial load is 1.1 kilonewton. Power loss is 3.3 kilowatt. So what is the viscosity and coefficient of friction? So these are all the two parameters unknown to us. We shall see that how to calculate it. Okay. So with the given data, first I will consider the frictional force equation. It is a 2 pi square neta n dash LD over psi. And also we know that power loss is equal to frictional force into velocity divided by 1000, where velocity u is equal to pi d n dash divided by 1000. Okay, so from this power loss is given in the problem. You have calculated the velocity, so you can calculate the frictional force F mu. If this frictional force is calculated, so use that value into this friction equation and calculate this unknown viscosity. Unknown thing, viscosity. Simple. Okay. So with velocity value calculated, it is coming out 80.63 meters per second. So just substitute this value into this power loss equation. And always you must be very careful with this equation. That is power loss equation. You must be always in meters per second. Okay, this value must be in meters per second, because this formula is derived considering u value in meters per second. Of course, you may put a d in millimeter, not an issue, but this formula is derived considering u value in meters per second, because so just compare the just have the dimension. Um, F is force is Newton, velocity is meters per second, Newton meter is joule, joules per second is watt. Clear? So that's what you must be in meters per second. So substitute that value and calculate the u value. And again, substituting back into this power loss equation, u value, I'll get coefficient of friction, that is 40.93 Newton. And substitute this coefficient of friction, frictional force, not coefficient of friction, frictional force. Substitute this frictional force into this Petrov's frictional force equation. I'll get the required value, that is viscosity. Just have this calculation from your end and tell me what is the answer. Theta is equal to 2.202 into 10 raised to minus 9 Newton second per mm square. So that is the viscosity. So one more parameter is to be find out, that is the coefficient of friction. So once the viscosity value is known to you, you can easily calculate the coefficient of friction. Simply substitution, that's it. But here p value is not given in the problem. Instead, they have given the load bearing capacity, I mean load applied, and dimensions of the bearing. So just use that dimensions L into D and load, calculate the pressure P, and substitute this pressure into this equation. coefficient of friction equation and calculate the coefficient of friction. So it is 0.037. So the problem is over. Very simple, no? So the problem is very simple. So like that, see, they may just shuffle the values from problem to problem. Okay. So one value, if it is given, they may ask for the other thing, other parameter. So like that, they can interchange the values and the parameters from problem to problem. So you must know the methodology of solving the problem. That's it. Okay. And one more thing, this one, we have a problem in aerodynamic lubrication considering the Sommerfeld number. Okay, so you know what is that Sommerfeld number? In the previous semester in the design of machine elements 2, we had a chapter lubrication and bearing there. We have solved similar kind of problems there along with the Sommerfeld number. We shall see that what is that Sommerfeld number and what is the significance of Sommerfeld number and how the problems are associated with Sommerfeld number in case of hydrodynamic lubrication. So I will discuss that in a separate class. Okay. So I will just rush through one more topic related to this hydrodynamic lubrication. That is hydrodynamic lubrication theory. Okay, so in this case, hydrodynamic lubrication theory, we shall see the mechanism of pressure development in an oil film, considering various cases, case 1, case 2, case 3, like that. Okay, so how this hydrodynamic pressure development takes place within the journal, we shall see that. First case, mechanism of pressure development in an oil film, considering the first case. So what is this first case? A flow between two parallel surfaces. So flow between two parallel surfaces. So this is the stationary plate surface and this is the moving plate. Okay, this is moving plate and this is stationary surface. AB is the stationary surface. It means bearing block surface, and this above surface is journal. When it is developed, the front view looks like that. When journal is developed, it takes the shape of the rectangular shape, and the below one is represents the stationary surface. I mean the bearing block, and the above one is journal. Okay, this gap is filled with lubricant, and thus the film thickness is H. And this fluid flow takes place by means of shearing action according to Newton's law of viscosity. So layer by layer the fluid flows. The particles which are associated with the moving plate will have maximum velocity, and the velocity of the lubricant comes down layer by layer, and it is zero at the stationary plate. I mean the bearing block surface. So this is the analogy of pressure distribution. I mean velocity distribution in case of hydrodynamic lubrication. So now we shall see how this pressure is distributed with this condition. Consider the case of the two parallel plane surfaces with an oil film between them. Let the upper plate A dash B dash, it is denoted by A dash B dash, moving with velocity u. It is mentioned of velocity u in the direction shown in the plate, and let AB be the stationary one. The velocity varies uniformly from 0 at the surface of the AB to maximum velocity u at the surface of A dash B dash. And the rate of shear throughout the oil film is constant. See, this shear rate is constant throughout the oil film according to Newton's law of viscosity. And as indicated by the uniform slopes of the lines A, C dash and B, D dash, B, D dash, assume that these surfaces are wide in the direction perpendicular to motion, so that the flow of the lubricant in this direction is negligibly small. That is, end flow is neglected. So under these conditions, the volume of fluid flowing across section A dash in unit time is equal to that following flowing across section BB dash. So whatever the oil flow that I mean fluid flow flowing at A dash is in unit volume, it is equal to that in B dash. And the velocity of a flow of oil film in any plane is proportional to the distance from AB. Proportional to distance from AB. Under these conditions, there is no pressure built up in the oil film, and the pressure at all points in the film is equal to zero, because the ability of a film to support a load depends upon the pressure built up in this film. A bearing with the parallel surface is not able to support the load by fluid film, and if any load is applied, lubricant will be squeezed out of the bearing and it will operate under extreme boundary condition. So this is a case of first case of pressure distribution. We shall see one more case. From this you can understand in a better way. One more case. This case. Look at this case 2. This is case 2. Flow between two parallel surfaces where AB is stationary while A dash B dash is moving in a direction perpendicular to AB. So earlier case, below one was stationary plate and above one was moving on right direction. Whereas in this case, flow between two parallel surfaces, AB is stationary and A dash B dash moving perpendicular. So this direction perpendicular to AB. So what happens in this case? The lubricant which are there between the plates, it gets squeezed out. Okay, so this pressure distribution, this indicates pressure distribution and these indicates velocity distribution. So in the examination, you may get a different question on this. Explain the mechanism of pressure development in an oil film, considering the various cases. So first case I have discussed. Second case is flow between two parallel surfaces where AB is stationary and A dash B dash is moving against the AB in a perpendicular direction. Just I will explain this mechanism. So consider two parallel surfaces, AB and A dash B dash, in which AB is stationary while A dash B dash is in motion in a direction perpendicular to AB. So there is no relative motion of the surface in the horizontal direction, and also and the end flow is also neglected, and the oil is squeezed so that if it is flowing both to the right and left of the section, that is the CC dash, the rate of flow is zero. In the middle section, CC dash. So it means that the rate of flow in the middle section is zero, and it gradually increases from point to point on either side. Okay. As the distances from center cross section increases, the maximum flow occurs at A dash and B dash. Maximum flow occurs at A dash and B dash. In each cross-sectional velocity of the oil will be maximum in the middle layer and zero at the surface. So this type of flow is possible if there is a pressure gradient. If there is a pressure gradient with the maximum pressure at the middle section. Say this pressure developed depends on three parameters. First one is viscosity, and the second one is difference in the rate of flow, and the third one is velocity with which surface A dash B dash approaches AB, and also the area of the surface and instantaneous clearance. So we shall see the third case. Third case. So pressure-based flow between the two parallel or stationary surfaces. So velocity distribution across oil film is same in different sections. So again, this is purely pressure-induced flow, where both the surfaces are stationary and the lubricant is flowing just due to the difference in pressure from one point to the other point. So this kind of a flow is called pressure based flow. So this is case 3. We shall see how the velocity and the pressure gets distributed in this case. See, in case of pressure based flow, the flow of the lubricant by a difference in pressure in a different cross section is called pressure induced flow. Another example of a pressure induced flow is that is shown in the figure. And here the liquid flows between two parallel stationary plane surfaces with the pressure P1 in section AA1 and with the pressure P2 in the section BB1. The flow is from left side to right side, and the velocity distribution across the oil film is same. Velocity distribution across the oil film is same in different cross sections. So this velocity u is given by this equation. That is 1 over 2 neta into dp by dx into t square minus y square. So you can use this formula to find purely pressure induced flow. Okay. Then this case, flow between inclined plane surfaces. Flow between inclined. Earlier, we have seen the flow between parallel plate surfaces. So in this case also, these two plates are parallel. And in case number 2 also, these two surfaces are parallel. And even in case 1, also these two surfaces are parallel. Let us see what happens when the flow between inclined surfaces takes place. This is a case, flow between inclined surfaces. So this is a flow between inclined surfaces where the below surface is inclined with some angle alpha, and the above surfaces is it is purely parallel to the reference horizontal reference line. Okay, and moving with velocity u, and the below one is stationary. See, in this case, in the case of non-parallel plane surfaces, where one is stationary and the other one is in motion with the constant velocity, and the direction in the other direction is negligible. So the volume of A dash, C dash. So this volume I'm talking about, A dash, C dash is greater than that of the volume of B dash, D dash. Just observe this. The volume of oil in the region A dash, C dash is greater than the volume of the oil in the region B dash, D dash by an account of AEC dash. What is the amount? This amount by an account of AE dash. It means that volume of A dash C dash is more than volume of B dash D dash by an account of volume of AE C dash. As the fluid is incompressible, so air is compressible, no doubt about it. Whereas the liquid one, it is incompressible, and there is no end flow. The actual volume of the oil carried into space must be equal to volume discharged from the space. And the excess volume of oil carried into space is squeezed through A dash. The excess oil gets squeezed through A dash and B dash, producing constant pressure induced flow through these sections. And this is a mechanism. And we have one more type, that is when this is where the below surface is stationary and the above one is moving. We have one more case where, that is in inclined case only, where both the surfaces are stationary. Below surface is also stationary, above surface is also stationary. So in this case, the velocity distribution takes place like this. Okay. And this case, pressure distribution as shown in the figure, and the velocity distribution is also clearly shown here. So likewise, you have to compare the various cases of pressure and velocity distribution from one case to other case. Okay, so probably you may get this marks for 8 to 10 marks. You may get this question in the examination. So just draw this diagram, neat diagram, sketch, and compare one case with the other one. That's it. Okay, just observe the previous year question papers where definitely in one or the other year you will be getting this question. Next, last topic that is theoretical topic in hydrodynamic lubrication is the mechanism of pressure development. Mechanism of pressure development. We shall see that. Okay, sorry, mechanism of continuous oil film. Mechanism of pressure development we have seen. So this is formation of continuous oil film. So after that, there is one big derivation related to Reynolds investigation. So I will take up this derivation in the next class, Reynolds equation. So I will just uh, explain how this oil gets continuous oil film gets created in the journal bearing. Okay, so I have four uh, steps. Okay, so or four with respect to different time horizons. Four stages. I can call it as stages. So this is stage one, or stage B, two. I mean B, stage C, and stage D. So this is journal. This represents journal, and outer ring represents bearing block, and this gap is filled with lubricant normally. And this is a journal which carries the load, the W. Whatever the load to be transmitted, that is purely carried by the journal. Okay. So in the second stage, what happens as the journal starts rotating? You will get a two. It can be divided into two portions. This is upper portion and this is below portion. And as the further the journal starts rotating further, again this portions get shifted. Okay. So like the convergent and divergent film, I can call it as. So when journal starts running at higher RPM, so it almost runs concentrically with the bearing block. Journal starts running almost concentrically with the bearing block. So there won't be any convergent and divergent areas. Okay. Uh, I'll just have an explanation. Just listen to me. So in figure A, the journal loaded by W is at rest, and the metal to metal contact is at the point N. So in point N, purely metal to metal contact. It means journal is in physical contact with the bearing block. As the journal starts rotating slowly and tends to roll up the bearing surface due to friction between the surfaces, that's how the point of contact moves to position M. As the journal starts rotating, so point of contact moves to position M. In this position, the continuous oil film consists of two parts, a converging part, above line ML. So above line ML is considered to be convergent part, and below line ML is considered to be a diverging part. So as the journal starts rotating at higher RPM, the positive pressure developed in the converging, the positive pressure developed in the converging portion moves the journal into the right side as shown in the figure, and this process continues. Okay, and further increase in the speed of the journal, it creates some kind of hydrodynamic action, and that hydrodynamic action is sufficient to lift journal from the contact of the bearing block, and the journal starts running almost concentrically with the bearing block. Okay, so this is shown in stage D. So this is the formation of continuous oil film. Here the oil film is not continuous. Here is also not continuous. At the fourth stage, the oil film becomes continuous. This is how the formation of continuous oil film takes place in case of hydrodynamic lubrication, especially in case of journal bearings. So this can be asked for 5 to 6 marks. Explain the formation of continuous oil film in case of hydrodynamic lubrication means. So you just take an example of general bearing and explain the formation of continuous oil film with your own words. Clear? Okay, fine. So next class I will take up this Reynolds equation, two-dimensional equation. So with this Reynolds two-dimensional equation, the flow rate in case of capillary tube, the velocity value, and also the other things, whatever the requirement, flow rate, velocity, pressure, everything can be calculated. Okay. So with this Reynolds two-dimensional equation, so I will take up this topic in the next class. So if you have any doubt, you can post a comment. Otherwise, I will end the session.